Hey there. Have you ever really thought about what happens right after you swallow a pill? It seems so simple, right? But what it really kicks off is this incredibly complex journey through your body. The science of that journey, it's called pharmacokinetics. And today, we're going to follow a pill's path to figure out exactly how our bodies handle the medicines we take. But let's start with a story. A true story that shows just how critical this journey really is. Picture this. A perfectly healthy young man takes a standard, over-the-counter cold medicine, and just 45 minutes later, he has a massive heart attack. It's a shocking thing to happen, and it raises this huge question. How in the world can a recommended dose of a common, supposedly safe drug do something so dangerous? To solve this mystery, we have to follow the evidence, and we're going to start with the case file. All right, so this case is all about a very specific drug and a very real clinical event that was actually documented in medical journals. So let's get into the facts. Okay, so let's break this down. The patient was young and healthy. The drug was pseudoephedrine, that stuff in a lot of decongestants. He took the standard recommended dose, exactly what it says on the box. And yet, 45 minutes later, he has a confirmed heart attack. There are no obvious red flags here, just a normal person, a normal dose, and a completely catastrophic result. That's the mystery we need to solve. To really get what went wrong here, we have to trace the exact path that pill took through his body. And this process, which is called oral absorption, is really the key to cracking this whole case. So that first critical step is called oral absorption. And in plain English, it's just the process of getting the medicine out of your digestive system and into your bloodstream, because that's where it needs to be, to travel around your body and actually do its job. But here's the thing, this journey is not the same for every single pill or for every single person. It's actually influenced by this three-way interaction. You've got the chemical makeup of the drug itself, the design of the pill, is it a tablet or a liquid gel, and of course, the unique biology of your own body. So with all this complexity, how do scientists even begin to figure it out? Well, they've developed these incredibly sophisticated models to map this journey and predict how a drug is going to behave once it's inside of us. There are basically two main ways they do this. The first is called the bottom-up approach. Think of it like creating a super detailed blueprint of the human body and then running a simulation of the drug moving through it. The other way is the top-down approach, which is more like analyzing traffic patterns. It looks at actual blood samples from patients and then works backward to figure out what happened. Just look at the level of detail in this bottom-up approach. This isn't just some simple sketch of a stomach. This is a model that breaks down the entire gastrointestinal tract into 9 distinct parts, from your stomach all the way to your colon, and each one has its own unique properties. It's just incredibly precise. Honestly, you can think of these simulations, they're called PBK models in the field, as a kind of SimCity for pharmacology. They're modeling fluid flow, biochemistry, you name it, all to predict exactly what's going to happen to a drug once it's inside your body. And what's the point of all this insane complexity? Well, it's to get this, a prediction of a drug's concentration in your blood over time. This curve is absolutely crucial. It's what helps determine if a drug is safe and effective long before it's ever given to a real person. And that concentration curve, that's where we're going to find the answer to our mystery. Because what's happening inside your body is really a dynamic race, a race between the drug getting in and your body trying to get it out. So, this is the crucial point. There are two competing forces constantly at play. You've got the rate of absorption, that's how fast the drug is entering your bloodstream, and then you have the rate of elimination, that's how fast your body is breaking it down and getting rid of it. When you first take a pill, absorption is totally winning that race. The drug is pouring into your system much, much faster than your body can clear it out. And if you look at a graph of this, that's the absorption phase, where the line is shooting upwards. But that climb doesn't go on forever. Eventually, the curve hits its highest point, and that point is called Cmax, or the peak concentration. This isn't just when the drug is most concentrated, it's the exact moment of equilibrium, where the speed of the drug coming in perfectly matches the speed of it going out. Right after this peak, elimination starts to win the race. Your body begins to clear the drug faster than it's being absorbed, and so the concentration starts to fall. Cmax is that all-important turning point. Okay, so we've got absorption, we've got elimination, and we've got this peak concentration, Cmax. That's great, but how on earth does any of this science explain a healthy person having a heart attack from a simple cold pill? And this is where it all comes together. Because this science isn't just some academic exercise. It has profound real-world consequences. In fact, it's the key that finally solves our case and explains how a common medicine could become so dangerous. And here it is. Here's our answer. The rate of absorption can be wildly different from person to person. Things like your own genetics, or even just taking a pill on an empty stomach, can make your body absorb it unusually fast. When that happens, the drug's concentration can spike, really spike, super fast and super high, pushing that Cmax into a toxic level. And a spike like that can trigger a severe reaction like a vasospasm, which is a sudden, dangerous tightening of a blood vessel. That's what caused this patient's heart attack. And the craziest part, it all happened before his body had even finished absorbing the full dose. So if you take one thing away from all of this, let it be this. A drug's safety isn't just about the dosage, the total amount you take. It's also about the rate, how fast your body absorbs it. A normal dose absorbed way too quickly can be just as dangerous as an overdose. Which kind of leaves us with one last thought, doesn't it? Think about the common, everyday medicines that are probably sitting in your own cabinet right now. Behind every single one is a hidden story of absorption, elimination, and that race to the peak. So, what's their story?